All right, let's jump in. Let's start talking about adrenergic drugs. Um, the reason why, also too, that I don't hide the complete version is because, people, it it it's up to you guys to know when to look at the complete versus like practice on your own. Like you know how to do that stuff by now. I don't need to um, police it. All right, adrenergic drugs. When we talk about adrenergic drugs, there's a couple of key pharmacophores that we have to talk about. And this vocab word pharmacophore is very, very, very important for understanding how certain drugs relate to each other. So the idea of a pharmacophore is essentially a key feature that causes a specific uh, uh, mechanism. We looked at this previously, right? So when we go back to the adrenergic, the cholinergic drugs, we saw that for acetylcholine-based drugs, you needed to have that ester, a couple of carbons, and then an N plus to work as a mimic of acetylcholine. So we could say that this ester, couple of carbons, N plus is the pharmacophore of cholinergic drugs. What we saw is that we can kind of run with this idea a little bit further. We can have some really funky structures that still mimic the same pharmacophore, where you have an ester, a couple of carbons, and a nitrogen that's positive. So when we talk about adrenergic drugs, they are primarily going to stay very, very, very similar to the pharmacophore that they are based off of. And when we talk about that, the first thing that we have to look at is how adrenergic neurotransmitters are made in the body. And what that starts with is tyrosine. Tyrosine is a naturally occurring amino acid. It has a benzene ring on it with this OH group on the end. Tyrosine, as we've seen previously, is metabolized into dopa, often just called dopa. You might also see it labeled as L-dopa. Oops, sorry, I put that in the wrong place. The enzyme itself is called aromatic hydroxylase, as we've seen previously. And the drug that comes out of this is called dopa. My bad. And so what happens is that we keep this same amino acid backbone, but we're talking about aromatic hydroxylase. So what can we guess about the function of aromatic hydroxylase just based on the name alone? Yeah, it's going to work on an aromatic portion of a drug, and it's adding a hydroxyl group. So we're going to be adding OH on an aryl group. By the way, you're going to see this abbreviation for me a lot, AR, which stands for aryl. It's the same thing as saying aromatic for all intents and purposes. So if you see AR from me, just know that we're talking about an aromatic ring. So what comes out of aromatic hydroxylase is our benzene ring with an OH para and then an OH meta. It's at this point that we start to close. It's at this point that we usually rotate this molecule so it looks a little bit different, but it ends up being the same structure. Tyrosine is normally drawn in this kind of vertical arrangement, but by the time we get to our monoamine neurotransmitters, we start to look at them in their horizontal configuration. Why? Just by convention. Just by convention. So often what you'll see is DOPA drawn like this. Did not leave myself enough room. There we go. Perfect. So this is the same structure. This is still DOPA. We just look at these generally in the more horizontal format. This then goes through the enzyme aromatic, oh God, I can never remember this one. Aromatic L-amino L-amino acid decarboxylase. Which is often just abbreviated to AAADC. Some people even just abbreviate it to the DOPA decarboxylase as well. But the reason why I spelled this out specifically is because any aromatic amino acid will get metabolized, which is exactly how droxydopa works, right? So I always like to keep it as its full name purely because a lot more drugs than DOPA decarboxylase go through this enzyme. So in MedChem pharmacology, I always say leave it as its original name. You can shorten it to aromatic decarboxylase, but don't focus on the name DOPA decarboxylase. That's kind of too much. Just like the name suggests, we are going to decarboxylate. And what's essentially going to happen here is that the carbon involved in our carboxylic acid is going to be taken off as CO2. So if we count, right now we have 1, 2, 3 carbons. So now we should only expect to have 1, 2, and then this nitrogen coming down below, along with our OH groups. At this point, we have created the amino acid dopamine. And the last step for the body is to add a OH group at the beta position. So again, we have another hydroxylase. So we're going to be adding an OH. And essentially, we have the alpha carbon here, and we have the beta carbon there. So we should expect to see an OH show up in that beta position. And specifically in the body, it always puts it on an R configuration. Naturally formed norepinephrine is an R configuration. For the exam, you need to be able to identify each of the structures and be able to label each of the different enzymes. So he could give you 5 random structures, and he could say which one of these is involved in the second step of norepinephrine synthesis. And you'd have to figure out which one is DOPA, which is why I have given it to you in its 2 forms. Does this make sense? Sweet. Now, we talked about earlier about this idea of pharmacophore. And what you'll notice is that by the time we get to DOPA, the pharmacophore that we care about has started to form. And that pharmacophore is the catechol, which is where you have a benzene ring with a 1,2 dihydroxyl group. Now, the 1,2 is more just relative positioning, that they are next to each other. But you can also have 1,3, you could have 1,4, you could have different arrangements going on that would not be catechol, but would be able to have a specific output for the body. So the big thing here is that we have this catechol functional group. The last part of the synthesis that you need to be aware of is what happens in the adrenal medulla, where norepinephrine goes through a enzyme called N-methyltransferase. N-methyltransferase. And essentially, all that's going to happen here is that our norepinephrine structure is going to stay exactly the same. All I'm going to do is just rotate up this amine into the position that it's normally just written at, which is, instead of it being written downwards, it's written upwards. But the positioning is still the same. And now you have this methyl group that's added on, and you have epinephrine. What'd you miss? The reason why I drawn it is because when you look at all adrenergic drugs, in some way, shape, or form, they need to mimic the catechol. So when we look at both epi and norepi, the big difference between epi and norepi is at the methyl group. Nothing to do with catecholamines, right? Nothing to do with this catechol portion. So because of that, this is why we get this crossover between norepi working on beta receptors as well as alpha, and epi working on beta receptors as well as alpha. And why there's some affinity one way or the other, but we have a bunch of crossover. It's just because we have a methyl group difference. Couple of other vocab words I want you to be aware of. The first one is phenylethylamine. Phenylethylamine is describing the three main portions of the norepi and epi structures. So you have your phenyl group, you have two carbons, your ethyl group, and then your amine. The phenylethylamine backbone is what mimics either epi or norepi. This is what fits inside of the drug, the receptor. So having this phenyl group about two carbons away from an amine is what enables a drug to mimic norepi or epi. Does that make sense? Sweet. Just want to. All right, sweet. The other thing that you're going to see, the other vocab word you're going to see a ton of is catecholamine, which again is just describing this structure. You have the catechol connected to an amine. So when we talk about catecholamines, all we're describing is neurotransmitters that have this catechol and amine backbone, which would be epi, norepi, and dopamine. The other thing I should have mentioned too is that dopamine does fall under the phenylethylamine backbone as well. It has the same phenylethylamine. So two different descriptors. The last thing that we should talk about is this prefix nor. Nor means lacks a methyl group. So the reason why epinephrine is called epinephrine is because A, we discovered it first. And so norepi is just lacking the methyl group of epinephrine. That's the only reason why it gets its name. So if you see NOR, it means lacks the methyl group of the structure. All right, let's dive in and let's talk about this good old stuff. All right. Alpha agonists. When we talk about the alpha agonists, they come in two major flavors. The first flavor is that we have imidazoline. Actually, the first kind is the alpha 1 agonist mimicking the phenylethylamine backbone. So this would be a drug like phenylnephrine. Just need to screen grab. There we go. Phenylnephrine. As well as the drug methoxamine. Methoxamine. So these two drugs, first of all, the main portion of them is that they have this phenylethylamine backbone. And essentially, this is going to enable the mimicking of adrenergic receptors. So because it can mimic either norepi or epi, it's going to be able to go towards the beta or alpha receptors. And we can see very clearly in phenylnephrine, put this in orange, that we have the methyl group, the N-methyl, which will mimic more of epinephrine. Epinephrine? Yes. Bean, bean, bean. I know. I need to like write it up here for myself. Can never remember it. Bean, bean, bean. What you'll notice about methoxamine is that it mimics as well norepi. Even though this nitrogen does not have a methyl group on it, there is this methyl group here, which enables it provides the same sort of characteristic of a nitrogen having steric hindrance from the drug. Most of them do in one way, shape, or form. We're going to look at a slightly different backbone that ends up mimicking the same thing. What's important to note here is that what we see is that we are missing this fourth position OH. And it's this lack of the fourth position OH that allows for alpha 1 selectivity. Great question. This is why. This is why. in order to have pure norepinephrine activity, you need to have this fourth position OH. So we have this N-methyl group to get us towards epi, and then we're furthering the selectivity towards alpha 1 by getting rid of that fourth position. The result is that we're basically taking a drug that looks sort of similar to norepinephrine and shoving it into the epinephrine box. That's essentially what we're doing. The other part that comes out of this is that, remember that when we have our catecholamines, both norepi and epi will get metabolized through two different amino acid enzymes, either MAO or COMT, MAO and COMT. Failing to have this fourth position OH decreases MAO and COMT metabolism. So do we expect phenylnephrine to have a longer or shorter half-life than epinephrine and norepinephrine? Longer. Much, much longer. Does this make sense so far?
Wait, so if we don't have that fourth position OH, if it's not free, that decreases the likeliness of the structure going through MAO and COMT?
Exactly. So two effects. The first effect is alpha 1 selectivity. The second is MAO and COMT decrease their metabolism.
Wait, so if we have that 4 OH free, it's going to be alpha selective.
No, so I should have put this in. Missing this position. So the fact that it's not here or here.
Gotcha. Okay. Thank you.
No problem. And yes, decreasing metabolism extends the half-life. And the half-life is just a way of looking at how long is the drug going to give its action. And it's going to give its action as long as it's not metabolized. Exactly. Yep. So as it turns out, in order to fit into MAO and COMT, you need to have both of these OHs to help coordinate the correct positioning of the catecholamine. And if you don't have both, then you end up decreasing metabolism. It can still go in there, but it's going to take a while. Takes way more time. All right. The other backbone that we can have is, instead of having this phenylethylamine backbone, we can have what's called an imidazoline backbone. So if we take a look at, oops, that's kind of too small for you guys. Let's try. These. go. So unlike the previous drugs, which clearly mimic the phenylethylamine backbone, these drugs use an imidazoline ring as their backbone. What's interesting about having this imidazoline ring is that imidazoline has a very, very high selectivity for the alpha receptors. Very, very, very high. So just like how we needed to have that uh, phenyl, ethyl, and then the amine, what these drugs are using is a phenyl ethyl imidazoline backbone in order to get to the alpha receptors. And when you have this imidazoline group, what makes you alpha 1 specific, alpha 1 selectivity, has to do with the groups that are connected to the benzene ring. For alpha 1 selectivity, you need to have what are called electron donating groups. Or EDGs. Essentially, what EDGs are going to do is they have a lot of electrons that they don't necessarily want. So these are things like carbons, aryl groups, nitro groups, NO2. So if your benzene ring, your phenyl group, is connected to purely carbons or another benzene ring or a nitro group, then you would be considered an electron donating. So when we look at xylometazoline, we can see that what's connected to the benzene ring? Carbon, carbon, carbon. When we look at naphthalene, what's connected to our original phenyl group? Carbon, carbon. Oh, look, it's in another aryl group. On oxymetazoline, we have carbon, carbon, carbon. I know, right? What's important to note here is that for alpha 2 selectivity, we need electron donating group, electron withdrawing groups. Or EWGs. And these are any atoms that are traditionally negative. So oxygen, halogens like chlorine, fluorine, bromine, nitrogen, sulfur, any atom connected to our phenyl group that is traditionally electronegative. So when we compare xylometazoline versus oxymetazoline, who is going to have the most affinity or selectivity, I should say? Who has the most selectivity for alpha 1? Xylometazoline or oxymetazoline? Xylo. Purely because for alpha 1 selectivity, we only want electron donating groups, but in oxymetazoline, we decrease that selectivity very, very slightly with this added OH group. What makes an electron donating group is that the thing connected to our benzene ring. So here's our benzene ring here. What's connected to it? The next bond is a carbon. Carbon right here. Same thing here. What's next? Carbon, carbon, carbon. What's happening in oxymetazoline is that we have some that are electron withdrawing. We have some that are electron donating, but then we also have this oxygen, which would be a electron withdrawing group, which is going to decrease selectivity for alpha 1. It for Jonna's question, does the oxy have like 3 carbons worth of blah blah blah? No, we just kind of consider them to be you know, it's all relative. So we know that xylometazoline is going to go towards alpha 1 because it only has donating groups. Oxymetazoline adds a withdrawing group, which is going to decrease that selectivity very, very slightly. But, it's still fairly alpha 1 selective. Does it? Okay. The withdrawing effect depends on electronegativity, but it actually has more to do with the lone pairs on the group themselves rather than like electronegativity, kind of. That is it has a lot to do with when we talk about like Friedel-Crafts, if you remember that from Orgo, but you guys didn't do that in Orgo because you had Poulos. So it is what it is. But good question. When we look at naphthalene and we rank the drugs on alpha 1 selectivity, naphtha is actually much, much more selective than xylometazoline because we're adding this other phenyl group, right? This other benzene ring. So if you stick benzene rings on, you're going to have tons of donating, tons and tons and tons. Xylo is just a bit better than oxymetazoline purely because you have this extra OH group. Question for you. Which drug will be metabolized fastest? Maybe oxy, maybe xylo. Who wants to justify their answer? Because the OH? Why does that matter? Yeah, exactly. So oxymetazoline has this open OH group, which allows for direct phase 2 metabolism. We're going to do a ton of practice during our review about metabolism now that we have actual drug structures to look at and different stuff like that. So we'll take a look at metabolism specifically later. So for alpha-1 agonists, we have two different types. We have the phenylethylamine backbone, which very clearly mimics our neurotransmitters, or we rely on the imidazoline group to force ourselves into the alpha receptors, and then we can choose alpha-1 or alpha-2 based on what is connected to that phenyl group. So when we look at our alpha-2 agonists, we expect to see very, very, very similar things, but electron withdrawing instead. Is this too small? Probably too small. Oh, I'm not gonna have enough room. Guanfacine. And aperclonidine. All right. What do we notice about these alpha-2 agonists? What kind of backbone do they have? Do we think they're phenylethylamine backbones or imidazoline? And these guys are all imidazoline. So the imidazoline backbone, just as a reminder, this is what's going to be alpha-1 or alpha-2 selective. And when you look at the structures of guanabens, guanfacine, aperclonidine, it's very clear, you know, who's here. But what you notice is that we still have this same sort of arrangement of nitrogens in guanfacine and guanabens. So even though it's not strictly locked in this ring, what we find is that this this functional group, all three of these carbons, all three of these nitrogens, which is called the guanidine group. The guanidine appears to be just as good as selecting for alpha as imidazoline. So whether you have the guanidine backbone, guanidine, or you have the imidazoline backbone, you end up getting similar results. What do we notice that's connected to our benzene rings? Do we have electron donating groups or electron withdrawing groups? Chloro, OH, yes, withdrawing. So we have EWGs, which is going to be alpha 2 selective. So each one of these chlorines is going to be very, very, very alpha 2 selective. And what's the effect of having this nitrogen connected directly to the ring? What is that going to do? Is that withdrawing or donating? It's also withdrawing. Yeah. So we have several different kinds of withdrawing groups here. All of them are going to make us very, very, very alpha 2 selective. The other thing that we should note about chlorine specifically, chlorine increases lipophilicity hugely. Very, very, very big lipophilic moiety on a drug. So because of that, where do we think chlorine is going to enable these drugs to go? Are they going to stay in the periphery, or are we going to be able to enter into the CNS? Into the CNS. So these drugs are all going to be able to penetrate the blood-brain barrier. The exception is apraclonidine. Remember, an amine is a basic functional group. So it can get, in acidic conditions, this nitrogen here will be protonated. And the NH3 is going to prevent absorption. Which, if you remember, where are we using apraclonidine? Is one very, very specific use. Very good guess. This is for glaucoma. Not a bad guess. Any questions about these drugs? All right. Is this making sense so far? Sweet. Sweet, sweet, sweet. Great question. The way that chlorine makes drugs more lipophilic is that essentially, if you look at the relative size of carbon, so here's carbon, and then we know that carbon is the quintessential, or actually I should draw it like this. Here's hydrogen, here's carbon, and these guys are the quintessential lipophilic atoms, right? When we look at chlorine, It's essentially just a big carbon. It's a very, very, very big atom. And so the reason why we increase lipophilicity with chlorine is because it's just so big. Yeah, big boy. Big, big, big boy. Put the Oh, he did put the okay. Timolol. I need to pay attention to which drugs he's talking about because he's like mixing up my old exams with your exams. All right. Uh, let's go on and talk about beta 2. Actually, no, we should talk about the alpha antagonists first. That's a better way of doing this. Oops. All right. When we talk about inhibitors or we talk about antagonists, the key thing about antagonists is that they have to mimic the structure enough that they can get to the receptor, but they have to lack a certain characteristic that would activate the receptor. So, in other words, they need to get to the receptor, but they need to not have such affinity for it that they end up activating it by mistake. The first drug that we're going to look at is one of the most simple out there, and it is tolazine and its brother, phentolamine. What we notice about these non-selective alpha blockers is that they have our imidazoline backbone, which, as we know, is going to give us alpha 1 and alpha 2 selectivity. But are they, for tolazine, does it have electron withdrawing or electron donating groups? Essentially neither, right? We need to have this carbon here in order to have it be connected. But in the case of tolazine, we have no donating groups and no electron withdrawing groups. When you look at phentolamine, how about on this benzene ring? Is this donating? Yes, because you need to have this initial connection. So we have an EDG down here, and we have a withdrawing group here. And so they end up balancing each other out, that you end up having neither. And this is what provides the antagonist activity. Does that make sense? Any questions about that?
So phentolamine, because phentolamine has both EWG and EDG, it's like canceling itself out pretty much. So it's an antagonist in the end, that which
Yeah,
causes itself being the antagonist.
exactly. The
Okay.
for phentolamine specifically, it 50% of the time it's going to alpha 1 because of the donating group, and 50% of the time it's going to alpha 2 because of the withdrawing group. Or that sorry, the reverse. Sorry. So it's but essentially it's equal. It's balancing its activity out. Only if it's equal. Right. There was a drug that had another OH here, and it was like a alpha 1 partial blocker, alpha 2 blocker. It was very, very weird. Um it's not useful at that point. Like you want a partial blockade of alpha 1, but you want to mostly blockade alpha 2. It doesn't make any sense. Could need to go on to the next. Wait until we get to the opiates. They have lots of that. You're a partial mu agonist, but a kappa antagonist. Selective alpha 1 blockers. When we look at the selective alpha 1 blockers, what is interesting is that actually let me double check on that. Yes. Yeah. When we look at the selective drugs, what we see, oop, I didn't even put the structure in for you guys. Here we have prazosin. Here we have terazosin. And probably the favorite of the three, doxazosin. What's your initial thought about how these drugs relate to alpha 1 agonists? Do they relate very well? Do they relate poorly? What do we think? They have some EDGs. I would agree. So what's important to note about these drugs is that they all have a different backbone to what we normally see. So let me take a picture of this. All of these drugs have this backbone called quinazoline. If we look in quinazoline, it's essentially like a kind of imidazoline, which is what enables our alpha 1 selectivity, or sorry, alpha selectivity. Uh, There we go. Just had to check on something. So, doxazosin, prazosin, and terazosin. What kind of alpha-1 antagonists are these? Are these selective or non-selective? What do we remember? They're 1A and 1B, right? The reason why they are 1A and 1B is that they all contain this piperazine group in the middle. For some reason, having this piperazine group is what enables circulatory selectivity. So in other words, this is what makes the drugs overall non-selective between alpha 1A and 1B. Does that kind of sort of make sense? Okay. The difference here is that when we look at a drug like tamsulosin, let me grab that structure. Oh, awful. When we look at a drug like tamsulosin down here, does tamsulosin have the piperazine ring? No, it doesn't, right? So tamsulosin, because it lacks that piperazine ring, makes it alpha 1A selective, which is why it's preferred for the prostate. Yep. Couple of other important features in here. Nope. It also does not have the quinazoline backbone. The reason for this is because it actually has the phenylethylamine backbone, right? So we have our phenyl group, our ethyl, and our amine. So tamsulosin, not a quinazoline, which is like an imidazoline, it goes back to the phenylethylamine backbone. Just to make it confusing, right? Couple of other important points I want you to be aware of. What is the effect going to be of these methoxy groups in terazosin, prazosin, and doxazosin? What's going to happen here? They're going to be the site of, they're going to be withdrawing groups, yep. But in terms of metabolism, they're going to be easy pickings, right? So the methoxy groups are easy groups for site of metabolism. What we also see is major metabolism based on the group over here. What functional group is this guy in pink? I think you guys had to. Furan. Specifically, this is a up here, same thing. We have our furan. This is a reduced for furan, meaning that instead of having double bonds, we have single bonds. How about this guy? Do we recognize this guy? I'm not sure why you would. You didn't have to know this, but it's called benzodioxane. Not one of your functional groups you have to know, but I'll point it out. As it turns out, having a single bonds here are going to enable easy metabolism. Wait. Yes. Yep. Easy metabolism. Why? Because we can easily stick an OH group on there, right? Very, very easy site to have metabolism. Stick an OH right there. Boom. Now your drug is metabolized. Having a furan decreases the metabolism of the drug in the same way that having a benzodioxane majorly decreases the metabolism compared to terazosin. So of these three drugs, who's going to have the longest half-life? Doxazosin. Why? Because it has the group that is least able to be metabolized. Does that make sense? Any questions about this? All right. Let's jump into our beta. All right. Yeah, sweet. Beta 2 agonists. As we know, in order to affect the beta receptors, what essentially we need to go for is norepinephrine. No, epinephrine, bean. I know. You're gonna hear me fuck it up every time. Look, I wouldn't be a good tutor if I got it right every time. I have to leave something for you guys to. And I'm just going to grab one more. Grab salmeterol. All right. A couple things first about all these drugs. Specifically, what backbone are we mimicking? What kind of backbone do we have? Phenylethylamine backbone. Specifically, we have the epinephrine backbone. So we have our phenylethylamine, and we see that our amine has some sort of some sort of group connected to it. And these are all going to mimic epinephrine, which is going to enable beta 1 and beta 2 selectivity. What's interesting is that in order to be beta 2 selective, what we actually prefer, it does say norepi, which has confused me to no end as I've stared at this and said to myself, I need to change this. I need to change this. So it should be epi backbone. I will upload a correction. In order to have beta 2 selectivity, what we actually need to have is the spaced out catecholamine. So it turns out that a 3,5 hydroxyl spacing, where this is carbon 1, 1, 2, 3, 4, 5, 6. So in other words, having these OHs slightly further apart is what enables beta 2 selectivity. The other possibility is that we have what's called a 5th position aliphatic OH, which is what's specifically going on in albuterol, in salmeterol, formoterol, all your ederols, all that sort of stuff. So whether you're a 3,5 hydroxyl or you're a 5 aliphatic hydroxyl, the effect is the same. We space out the OHs and it drives us more towards beta 2 selectivity. What really comes down to then is the effect of what we're sticking onto. Does it not matter if it's not directly attaching to the OH? It'll aliphatic. All the drugs that fall into this category, it will be one carbon, then the OH. For all the ederols, like vilanterol, formoterol. Yeah, good question though. One of the big issues when we look at these drugs, right? You inhale the drug. Yes, more lipophilic, more affinity, definitely. And the reason for that is because we inhale the drug into our lungs. So, here is our lung, the lung air, shoo. And the drug initially will come in and be in the air, right? Shoo. What is lining our lung are epithelial cells. Beneath the epithelial cells, we have smooth muscle. are we trying to affect the epithelial cells or the smooth muscle when we treat asthma? What are we, the smooth muscle? So in order for this drug to get through, it has to pass all the way through one whole cell in order to then pass into a second cell to get to the beta 2 receptor, which is a really, really big task. So what that means is that these drugs need to be fairly lipophilic in order for them to get to the smooth muscle. But what are all these different groups? What do we have here? OH, 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 NH. These are all very polar, which means that they're hydrophilic, right? So is metaproterenol going to have a very easy time getting from the lung airspace into the smooth muscle? No. So this is where we have our tail group. In order to facilitate the drug getting to the smooth muscle, we need to increase the lipophilicity of the drug. So metaproterenol uses an isopropyl group, which barely enables it to get to where it needs to go. Terbutaline takes that step one piece further using a tert-butyl group, which, by the way, this is where the name comes from, tert-butyl. And that allows the drug to have more lipophilicity. Albuterol and salmeterol, same thing with albuterol. Albuterol uses the tert-butyl group, which enables it to have very, very good lipophilicity. But salmeterol, even more so. Salmeterol has a huge tail, huge lipophilic tail. So out of all these drugs listed, who's going to have the most lipophilicity? Who's going to be able to get to the receptor better? Salmeterol. What is the drawback to having this bigger group? What's the drawback to having this giant group? Dissociation, kind of. Heavy molecular weight, that is definitely a good point. Metabolism. Yeah, these are all great places to metabolize, right? So as you make the drug bigger, you make the drug more easily metabolized. So even though we have a drug that is very, very good at getting to where it needs to go, salmeterol, unfortunately, is easily metabolized. Any questions about that? Does that make sense? All right. Beta 1 selective. Um, beta 1 selective is right here. Or I guess I should say beta agonist, rather. So beta 1 agonists. The two drugs that we're going to look at, dobutamine and isoproterenol, once again, have the epi backbone. I labeled it wrong in the guide. My bad. Which is going to enable beta selectivity. What do you notice about what's the main difference in terms of the phenylethylamine backbone? So only looking at the phenylethylamine backbone, what's the biggest difference between isoproterenol and dobutamine? It's the same length of chain. So it's actually still same two carbons. We'll talk about the tail in a second, but what do we notice more about just in the phenylethylamine backbone? Yeah, it's missing an OH. So the missing OH in dobutamine is what makes this drug beta 1 selective. So isoproterenol is beta 1 and beta 2 non-selective, whereas dobutamine is beta 1 selective. You all put O. Oh. You all said O. What is the effect of having this massive tail for dobutamine? What would the effect here be? Exactly. What we find is that for catecholamine drugs, right? So these are drugs that are either alpha or beta, going to the alpha or beta receptors. When you increase the lipophilicity of a drug, you become more beta selective. The other thing that this is going to do is it's going to enable oral dosing. Although, because dobutamine is really used in a hospital setting, we don't really use it like that. So dobutamine specifically, it's given by a by injection most of the time, purely because it's used in like emergency situations, sort of thing. What is the issue with having this OH here? Metabolism, direct phase 2. Very nice. All right. What is based? I don't know what based is. I'm only like 2 years older than you guys, and I like Sag, Pog, Man Baba. I wish I knew what all these words mean. Yes. No problem. All right. Let's talk about beta blockers. Great question. Would isoproterenol be able to go through direct phase 2? Yes, it would, based on this OH here. Yep. The reason why I didn't point it out is because this is part of part of epinephrine, so it's not necessarily special. Would these be used for direct phase 2? How come? Why not? Exactly. These are going to go through catechol ol methyltransferase, right? Remember, these are all catechols. Double slave, double base, double pog, double sag. I don't know what any of these mean. Am I going to find out that there's slurs or something like that? Man, my recordings must be weird to listen to. Definitely not like class. All right. I want to look at one example, and then we'll talk about all the different substitutions and blah, 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 blah. But honestly, really, they all the beta blockers, they do the same thing. Remember that in order to be an antagonist, you need to mimic the structure close enough that you get to the receptor, but you need to lack a specific moiety in order to not activate the receptor. Because of that, what we get is the beta blockers, which are primarily trying to mimic the phenylethylamine backbone. That's really what they're going for. So, couple of things here. What we notice is that generally we have the phenylethylamine backbone. What you can see, sorry, I'm just looking at the textbook while we're doing this to make sure I'm not missing any big points, is that the phenylethylamine backbone is what's going to enable adrenergic activity, so beta and alpha. And then what specifically in propranolol is going to enable it to go towards the beta receptors? What's in propranolol that's going to enable it to go towards the beta receptors? Remember that when we talk about these, beta is epi, alpha is norepi. And what's the major difference between epi and norepi? Yeah, the substitution over here, right? So the fact that we have this isopropyl group is what's going to enable beta selectivity. So the phenylethylamine backbone gets us to adrenergic. Isopropyl, the fact that it's there, the fact that there's something here gets us to beta. And what's important about these drugs, and I'm just going to grab another one just to show comparison. There we go, atenolol. In order to be beta 1 selective, what you need to have is a substitution at position 4. So having a 4th position substitution is what enables beta 1 selectivity. So propranolol is non-selective, does not have a substitution at the 4th position. Atenolol is a beta 1 selective antagonist. Does that make sense?
So if you don't have something, you're beta selective, pretty much.
Right. You go to beta 1, you go to beta 2. You're a non-selective
Okay.
beta antagonist.
Okay.
So if I grab a random drug here, like Pindolol, exactly. Beta blockers do not have catechol functional groups in them, right? But they do mimic the phenylethylamine backbone, which is what allows it to go towards the adrenergic receptors. So does propranolol get metabolized through COMT? No. It's because it doesn't have the catechol moiety in it. So looking at Pindolol, so we can say that propranolol is a non-selective antagonist. Atenolol would be beta 1 selective. How about Pindolol? Non-selective or beta 1 selective? Non-selective. How do we know? Because 1, 2, 3, 4, nothing is there. I always like to show this drug purely because it has a triangle in it, and we don't see a lot of triangles in medicine. Betaxolol. Beta 1 selective or non-selective? This would be beta 1 selective. Because of the 4th position. Exactly. So it does not matter what is there as long as something is there. Um, Choo, choo, choo. Ba, ba, ba. Yes. Yep. And I believe that is everything on the exam. For the most part. There's a couple of things I skipped, mostly because they're clearly explained in the guide. Actually, did I skip anything? I don't think I did. I think I hit pretty much everything. If I missed anything while you're going through this, let me know. But I believe we only needed 4 hours to the exam. Good question. In the guide for the beta drugs, I put norepi background, but it should be epi backbone. So I'll make a comment on the classroom. We'll do that. Any questions about what we went over today or anything like that? All right. Well, let's finish up a little bit early. For a couple of things to note, please. In here, you will see a question about adding another day to the weekly schedule. So already we do Monday, Wednesday, and then if we need an extra day, I throw in Sundays. Let me know if you prefer a Tuesday or a Thursday extra session. For this week, wait, I was showing the right screen. For this week, you have an exam on Wednesday and an exam on Friday, right? Yeah. So for this week, we're gonna do Sunday, Monday, Wednesday, Thursday, and I'll make that announce. I'll post that up. Tomorrow we are going to do Thera. So we'll get through the kind of beginnings of Thera. It's really not that bad, all things considered. And I'll put together some patient cases and all that kind of good stuff. You got this. Don't focus on the days. Just focus on the total amount of hours you have in a week. Right? Plus, it's not, first of all, it's not that you have one day, right? You have all of Thursday to study, but you have all day after MedChem to study as well. You get 2 days to study. Bitching about one day. I know, retention. Class at 2, yeah. So you get out by like 3 to midnight. Boom, 9 hours. Look, if I could do it, you can do it. You can cry and complain during Thanksgiving. Like, that's fine. All right, everyone. All right, have a good night. I will upload this as soon as it tells me it's ready to upload, and then we'll be all good.
All right, thank you, Gabe. Good night.
No problem. Take care, everyone.